Hello everybody! Today I'm going to explain the solutions to the first 5 problems of the Educational Codeforces round 161, a round that took place yesterday. And I'm going to start in this first video by explaining the solutions to the first 3 problems, problems A, B and C. And then in another video that will be published at the same time with this one, I will explain the solutions to the problems C and D. So let's begin with problem A. So here we have 3 strings and we have this definition of a template. And basically we know that if the template has a lowercase letter, the letters must be the same. Otherwise they must be different from the lowercase version. So A uppercase and A lowercase can't be together in this case. So we now want to find if there is a template such that A and B match with it while C doesn't. And for this problem, it may be tricky at first because you read about templates, you might think about what kind of patterns you could see and stuff like that. But it turns out that it's just a matter of checking one case and making sure that there is at least one position in which we can differentiate the first 2 strings from the third one, because on every other position they can all work together. We don't care as long as there is one position such that the template no longer fits with the third string. And this is what I did in the solution. So basically I read the strings and I basically checked if there is at least one position such that both the character in A as well as in B are not equal with the character in C. Take note that for the sake of this argument, A and B can be equal. It doesn't really matter. They, as you can see, are treated the same. And this problem can also be solved with way more complicated solutions such as ZP or other kinds of constructions, but it was not necessary. However, if you want to avoid, let's say, overcomplicating casework for this problem, sometimes implementing a more complicated solution can be helpful. But you should still make sure to think at something easier. Now let's continue to the next problem. So we talked about the problem A. Now in this problem we have n sticks and we know that the length of each stick is 2 at the power of the value in the array. And we want to choose 3 sticks such that we can form triangles with them. And we want to compute the number of ways to do this. Now this problem, if the length of the strings were not, let's say, powers of 2, is actually a very well-known one. And it can be done by fixing 2 lengths and then binary searching the possible lengths that the third side of the triangle has. This can be probably found on every online judge out there. There are many such problems and the solution is also very well known. However, in this problem we are dealing with powers of 2. And now let's think about it. So we basically want to find 3 values such that we can form a triangle. So as you know, for every way to write these 3 values, we must make sure that A plus B is greater than C, A plus C is greater than B, and also B plus C is greater than A. Now let's take some cases. So what if, let's say, we have all of the 3 values distinct according to our problem? So we would have 2 at A, 2 at B, and 2 at C. And A, B, and C are all distinct. Without loss of generality, we can say that C is greater than B, which is greater than A. Now, there is a very important theorem that is used in many of these problems. And this theorem will be the bedrock behind the solution for this problem. So the theorem I'm gonna state is that the 2 at n is equal to 2 at 0 plus 2 at 1 plus everything up to 2 at n minus 1 plus 1. This means that, in other words, a power of 2 is greater than the sum of all other powers of 2 before it. So in this case, if we were to do this, this triangle would always be degenerate. So we can't have such a triangle. In conclusion, we now must have at least 2 equal sides. Now let's also analyze another case. Let's say that we have 2 at A, 2 at A, 2 at C. This triangle wouldn't even work either, because according to the same rule, if A is smaller than C, then the base case would be that these two added up would be equal to this one, which would form a triangle, although it would be a degenerate one. So this doesn't work either. So after these two observations, we now concluded that the length of the sides which are equal must be the maximum one. So this leaves us to two cases. We either have something like 2 at A, 2 at C, 2 at C, or 3 that are equal. Now let's take each case separately. So for this first case, so 2 at A, 2 at C, 2 at C, we now basically have, let's say, if we know that the frequency of C is Fc, and we know the frequencies of everything before it, we can say that it's something like Fc of times Fc minus 1 over 2 times a prefix sum that goes from 0 to A minus 1. So a sum that's I from 0 to to C minus 1 of F of I. And this can be computed in a rolling basis with the prefix sums, and also this other sum, the 3C's, it's basically just Fc choose 3. So Fc times Fc minus 1 times Fc minus 2 over 6. And these formulas can be put now together to achieve the outcome we desire. And this implementation is not too long either. So we just find the frequencies and apply these formulas separately. Take in consideration that we want to avoid overflows. So you should be very careful about that. Now let's move on to the third and the last problem we are going to discuss in this first video, which is closest cities. So in this problem, we are given a bunch of cities, and we now want to make sure that we have this way to traverse them, and we have this graph now. So we can either travel to any other city or the closest city. So we now want to process distance queries. Normally, this would be a prefix sum problem, but we need to deal with the closest city part. And actually, it turns out that given that there are no changes, we can easily treat the closest city parts by just having some if statements that exist together with the prefix sum construction. So instead of just adding the distance between two adjacent cities, we can add the distance between we can add 1 to the previous distance, and just make sure that we use the prefix sums properly. And after doing this, we are now sure that the solution will work. So it's just a very simple prefix sum exercise. So now, very important here to add the values properly. Some people got hacked by having negligent bounds here, like 2 billion or 1 billion or whatever. Please be careful with these in the future. It's very important to avoid getting hacked on a problem we completely solve. Now we construct the prefixes and the suffixes, just like I mentioned, either +1 or plus that distance. And now based on these cases, we can now simply derive the answer as being the answer for the suffix or the prefix based on the whether, let's say, now have to go to the left or to the right. So just as a classical prefix sum exercise, but with a little twist, with these ones instead of the actual distances. Now If you enjoyed watching this video, please like the video, subscribe to the channel, and share the content to your friends and everyone who wants to solve more competitive programming problems and take part in competitions and learn new things. Also, make sure to once again express your feedback in the comments. I reply to every comment, and I want to make sure that the content is as good as possible. So once again, thanks for joining this video, thanks for watching it, and also check the recommendations I have in the description. See you soon. Cheers.